All right, everyone. Well, I'm just going to say a few words about our honored guest, and then the stage will be Frank's for 40 minutes. So I think we're all really looking forward to the talk. I've just left this slide up from the AGM, just to let people, any students who weren't there, just to know that we do have some bursaries that are available to look on the website. And then obviously each year we do hand out the Barrow Award, and as we know, this year was Frank. And when this was announced on the sort of various email servers around the world, I got a lovely message from Bruce, who I'm really pleased to say is here. And he sent through this photo. And he also said, here is a picture of Frank in 1985 on Hal Helgason's notorious Greek NATO meetings. I'm not sure why it's notorious. He said, Tim Holland was there and can maybe tell you more than I can recall because he was often sober. Yeah. And then another anecdote, the 1992 Goldschmidt Conference was held at a resort near Reston, Virginia, and one of the bars boasted a football table. One evening I recall that Frank held off all comers at the table, including Dave Pryor, then a graduate student whose attendance was funded by the MinSoc. In his report on the trip published in the MinSoc Bulletin, Dave wrote a cautionary note: whatever you do at conferences, don't try playing Frank Spear at table football. So yeah, I've actually been meaning to. I don't know if you're still around tonight, but I'd be keen to give you a game. So, but no, so obviously there's some more serious things to say about Frank as well. So if you don't mind, I'm just going to read the citation that we wrote for the website in case some of you didn't see it. So yeah, it's with great pleasure we announce that the winner of the 2023 Barrow Award is Professor Frank Spear. So Frank is a professor of geology and head of the Earth and Environmental Sciences Department at the Rensselaer Polytechnic Institute, USA, where he's been based since 1985. So Frank completed his BA at Amherst College, Massachusetts in 1971, and his PhD on phase equilibria and mineral chemistry of a hydrothermally synthesized amphibolite at the University of California in Los Angeles in 1976. So Frank is widely known for his classic Big Blue textbook, and I didn't to bring mine with me, but it's a big thing to carry on the train, yeah. So the Big Blue textbook, Metamorphic Phase Equilibria and PTT paths, which galvanized the field in the mid-1990s, as well as for his pioneering contributions across multiple aspects of metamorphic petrology. At the time Frank started his research, quantitative metamorphic petrology was in its infancy. The first thermometers had only just been proposed with little direct experimental support, and most research relied on broad categories of conditions, green schist facies, amphibolite facies, etc., for quantification. Together with his students, Frank has been one of the most influential scientists in the field of quantitative metamorphic petrology, with major contributions including, and this is quite a list, major and trace element thermometry, metamorphic phase equilibria of major and trace phases, inversion of chemical zoning to determine PT paths, use of trace element zoning to infer reactions and help put the little t in PTT paths, calculation of cooling rates from diffusion profiles, identification of potentially significant overstepping using QuiG barometry, development of sophisticated thermodynamic modeling software, especially program Gibbs and thermobarometry, and development of tectonic interpretations of collisions and core complexes. So it is difficult to conceive how one individual can have such an impact on so many fundamental and current research areas of petrology. Therefore, the Barrow Award, which as you can see recognizes a scientist who has made outstanding contributions to metamorphic studies, is clearly most fitting and deserved recognition for Frank. So without further ado, I'd like to give Frank his Barrow Award, which you'll note is not from the Barrow zones. There was some discussion that we thought we'd be hostages to fortune if we started giving out different Barrow zones, because if we gave someone a garnet zone and then someone else a kyanite zone, like, is there some kind of ranking there? So we've just stuck with a nice metamorphic rock. So it's my great honor to pass this on to Frank. And
beautiful.
Yeah, and and thank you, Catherine, for organizing the.
This is from Escort Zone.
Simon Cuthbert, is he here? Yes, you picked this up, didn't you?
Yes, yeah, from North Fjord in Norway, in the Western North. Yeah, I think I've been there.
We got a piece to take home. And just finally, I'd like to thank Lorraine Terrell, Maria Tedeschi, and Victor Guevara for judging the awards. And I'd like to thank Matt Cohn and David Patterson, Phil England and James Salverston for nominating Frank. Because obviously we need people to do both. Really appreciate it. So I've said enough. I'll hand you over to Frank and I'll just let up your talk.
Well, you mentioned the Big Blue Book, and then you listed a whole bunch of things. The reason I wrote the book was because I've forgotten almost everything I wrote in there now. So at least I have a place I can go back and that's all I do. Thank you. Well, I'm truly honored and delighted, and a bit humbled to have received this award, because I think there's any number of people in this room right now who are equally deserving of receiving the Barrow Award. But I'm totally thrilled that you picked me. This is just, and I'm very glad that I could come to this meeting in person, because I've renewed a lot of old acquaintances, drank a few beers with people I haven't had beers with for a long time, and met a number of wonderful, I'll call you youngsters, but young scientists who are just blazing trails. And I'm in part I'm envious, but I noticed when I first looked at the MSG, after Owen contacted me and told me about the award, I looked at the website and I said, oh, wow, it's going to be great. Oh, and look there, they say they're going to honor a late career scientist. I thought, I wonder who that is. Well, actually, the more I thought about it, the more I don't mind being a late career scientist. It means I could retire sooner, which wouldn't be bad. But no, it's a tremendous honor. I'm so glad I could make it here and get to meet a whole lot of you people. So on to my talk. The rocky road to equilibrium. Well, equilibrium, I think everybody would agree, it's kind of our friend, right? I mean, who doesn't love a real beautiful pseudosection? I mean, these things are something that we create and we use to interpret our rocks. I think we would all agree that rocks don't evolve unless we kind of get out of equilibrium a bit. But there's somewhat of a tacit or explicit assumption in most papers that we're proceeding at a steps that are only a little bit out of equilibrium. So, the rock changes P and T and we're out of equilibrium. It gets quickly back there. And if that's, and that may well happen in a lot of places. I'm not saying it doesn't. If that does happen, then really the rate limiting step in the whole process is how fast you're changing pressure or temperature, which is perfectly okay. But some of the work we've been doing lately in my lab suggests that at least under some circumstances, and specifically here I'm going to talk about garnet nucleation. Under some circumstances, we can get pretty far out of equilibrium. And so the question is, how far out of equilibrium can we get? And that's going to be the first half of my talk. And then the second half is this crazy idea about how to model maybe how we can get back to equilibrium. You'll see where that goes when we get there. But let's see, I want to try and if I right click on this, I can say pointer options. There we go. Oops. Well, that'll go.
You just turned it off. You were a laser pointer.
What's that?
I put the laser pointer on, so if you wanted the pointer.
I just turned it off.
Yeah.
That's what you get when you bring a late career scientist. Okay, there we go. Anyway, so then how do we get back? And I think, well, you'll see. I hope you don't think I'm losing my mind when we get there. Okay, so in our lab we've been doing two specific things. We're applying QuiG barometry and zirconium-in-rutile thermometry to try to infer the conditions at which garnet nucleates and grows. This is a very typical Barovian garnet zone rock from Vermont. And when we do these things, well, the QuiG barometry, as you well know, gives you an isotherm along which you can say that the quartz inclusion was included in garnet, which has a nice gentle slope. The zirconium-in-rutile, we're looking at rutiles that are inclusions inside of garnet. So the interpretation is that the garnet must have grown after the rutile was there. And so it provides a lower limit on the temperature. So there's the zirconium-in-rutile line, rather steep. And that's the minimum temperature at which garnet could have nucleated. Well, we then compare that to the calculated garnet-in reaction, which is in this diagram shown in red. And you can see it's somewhat above it. And then we can do, well, exactly what Pierre was talking about earlier, and calculate the difference in free energy from a garnet-free assemblage here to a garnet-buried assemblage. And we're calling that the affinity, the same as CS. I want to say at this point, don't necessarily equate these numbers with the ones we found out over lunch that we're normalizing our results differently, but we'll work that one out. But anyway, compare this to the other numbers I'll tell you. Anyway, this is a reasonable amount of affinity. This is per 600 joules per mole of oxygen, normalized to the oxygen, one oxygen. We found this in typical Barovian rocks. We've also found this in blue schist. Here's a sample from Greece. Two samples and a nice photomicrograph. The QuiG results are there. The zirconium-in-rutile and over here. And these record affinities on the order of a few hundred to almost 1,000 joules per mole of oxygen. So it looks like things are overstepping considerably before garnet forms. Now, I was looking through my sample collection one day, and I really back in 1979, I collected these two samples. I've actually worked on the one on the right quite a bit, but I had forgotten about this one on the left. I remember the day I collected it, which is a weird thing, you know, what, 40 years ago. But you can see that the two rocks have very, very different garnet densities and garnet sizes. So this thing on the right here, this Politic schist, is a typical garnet biotite storolite kyanite rock, and it has, well, we measured 7 garnets per cubic centimeter, you know, plus or minus. This one on the left here, it's a hornblende biotite, plagioclase garnet. It's got some epidote in there. This thing has 3 million garnets per cubic centimeter crystal density, which is obviously quite a bit different. But they come from the same area. They went through the same PT history. And that kind of seemed, okay, something's got to be going on here. Here's an even more extreme example. There's a nice, you know, garnet zone politic rock with garnets. So there's one that has 30 garnets per cubic centimeter. This one on the left is sort of a quartzite, but it has amphibole in it and some epidote, plagioclase. And this one, if you can believe it, has 200 million crystals per cubic centimeter. I mean, that's a cubic centimeter, right? I find it hard to believe that there's 200 million crystals in it. But if you do the math and the crystals are all, say, 10 microns across, you get 1 billion out of that. You just do the division. So that's, I think the number's okay. We measured it several times. Anyway, why do we get this extreme amount of crystals in some rocks, and then other rocks from the same area, we only get a few large crystals? Well, clearly the nucleation rate exceeds the growth rate here and so on and so forth, but why does that happen? So since we're looking at the number of garnet nuclei, we turn to nucleation theory, and this is classic nucleation theory. I don't want to imply that I think this is the answer in metamorphic nucleation, but it's a place to start, and it, you know, shows that the rate is got to be exponential, and then there's this activation energy and this exponential relation. Well, you've all done this derivation, I'm sure. You know, you could take the activation energy as a sum of a volumetric change of the free energy with R cubed, so it's volumetric, and the surface energy, which goes with R squared, and you plot those things up on a energy versus radius diagram, and you find the surface energy continuously goes up. It's a positive number. The volumetric energy goes down. It's a you know, it's a negative value. This is exactly equivalent to the affinity that we're calculating when the garnet nucleates. So we have that number. What we want to know is what this critical radius is, and that's the maximum of the sum of the two terms. So we differentiate and we get this thing. This is, you can get all this stuff right out of a Wikipedia article. So don't think I invented it all. But anyway, you then plug this back into the activation energy. You get the activation at the critical nucleus, and then you plug it into the rate equation. What you find out is that the rate is a function of the surface energy cubed divided by the volumetric change of free energy squared. Now, I've ignored the strain energy here, but that's another term you can put into this. So here's a term for the rate of nucleation with a couple of terms in it that we don't know. We don't know the pre-exponential, we don't know this. But, and what we measured in the rocks are the number of crystals. So in order to get the number of crystals out of the rate, you have to assume some time frame. And here's a big gap in the whole analysis, but what we did was essentially, let's assume that all these rocks we're looking at nucleated at over the same length of time. So you multiply delta T, and then you get the number of crystals, and that's equal to this. So what we know in this equation is the delta V of the volumetric change of free energy. We don't know the surface area, the surface energy. We don't know the pre-exponential. But what we did was then plotted it all up. So there's the equation again. We plotted it up. The x-axis is the affinity. Now here it's been changed to joules per cubic centimeter because that's the units that you need for this. But here's the number of nuclei, and here are the garnets with only a few nuclei per cubic centimeter, and here's the one with extreme values. And they plot on this, there's some functional relationship there. Well, when we take this equation and try to apply it to this, it turns out that the pre-exponential is limited by the maximum number of crystals, which is around 10 to the 7th. So that number actually was easy to fit just by eyeball. The surface energy we don't know. The affinity we do, because that's here on the x-axis. But the surface energy changes the curvature of this. If you play with this equation, you'll find you can change the curvature. And all we did was an eyeball fit by juggling the numbers around, and came up with a value for the surface energy of 0.015 to 0.022 joules per meter squared, which interestingly is right within the ballpark of what other people have cited for surface energies for crystals. In fact, it's even much better constrained. The last paper I read was something like 0.1 to or like 0.001 to 0.2, and this thing is far. I'm not quite sure what to make of that, but anyway, it's well constrained. The difference between these two plots, if you're interested, is we did the top calculations of affinity with SPAC, and the bottom one with the HP11 DS6.2, and the only difference is the affinity. As you all know, depending upon what database you use, the garnet isograd shows up in quite different places. And for what it's worth, the HP11 dataset is about twice the affinity. I'm not going to make an argument about which is correct. If you want to turn these into affinities per mole of oxygen, you have to multiply by about 10. So here we have these rocks with lots and lots of garnets with very large crystal densities and calculated affinities, which range, well, in this one from 3 to 4, 5 kilojoules per mole oxygen. In this one, 3 to 6. Those are large affinities. And it'd be interesting to see how they compare to what Pierre was talking about and with affinities for the continuous reactions he was showing. But those are huge. And one of the things I would love to know, if this is all correct, is why was nucleation inhibited in these rocks to allow the affinity to build up to that point? I don't know the answer to that. The rocks don't look like they should have inhibited nucleation. Maybe this quartzite would, but certainly not this amphibole. And it may be that there just aren't enough good sites for the nucleation to occur. It may be that nucleation really doesn't want to happen. You have to get all the right elements in the right place. And one of the questions we got as an open question now is, it looks like these nucleated at the same time. The coarse ones and the fine ones nucleated at the same time. If that's true, it kind of suggests there might have been some trigger mechanism. And we fancifully put in the paper that the trigger mechanism could have been something like an earthquake or a boloid impact, of all things, which I think would really change the nature of our science if we could go and look at things like this and say, oh yeah, there was a boloid impact. But don't quote me on that one. Anyway, but the next question is, okay, so we have these rocks that have no garnet, then all of a sudden they nucleate garnet far out of equilibrium. What happens next? Well, clearly they want to get back into equilibrium. And the rest of this talk is my crazy idea about how to maybe think about that. Okay, so this was sort of inspired, I don't know, 40 or 50 years ago. Dougal Carmichael's paper on the mechanism of prograde metamorphosis. I'm sure you've all read this. but to review, what he was noticing was that in a rock where kyanite was being replaced by sillimanite, the kyanite was actually being replaced locally by muscovite, and the sillimanite was growing in muscovite elsewhere in the rock. And then there was a transfer of potassium from one place to the other, and protons or water back and forth. So this is essentially, you know, two independent open system reactions. And it also, he didn't make this explicit, but this is also a process that's rate limited by the transport of material. He assumed that aluminum was essentially immobile, but potassium was highly mobile. So I always love this paper, and I don't really think too many people have taken this too much farther over the years, at least not exactly in the kind of context Dougal did. Anyway, one of the things Dougal mentioned was that there was this problem with this particular reaction that he used was that there's an excess in volume. And one of the things he also noticed was that these textures never show any deformation there. They don't look like there's a big volume change. So he said, well, you get rid of silicon, that would solve the problem. I choose to solve the problem in a different way, but we'll see how that goes in a second. Okay, so that was sort of the inspiration. I also have my own rocks from Western Massachusetts that have these kind of textures. Here's garnet being replaced by muscovite and biotite, and it's a decompression reaction. These rocks were at 10 kilobars and then went down to around 3. And the overall reaction is kind of Schermack exchange sort of thing, garnet plus muscovite going to biotite plus plagioclase. And yet, well, and the reaction consumes muscovite, and yet it's growing selvage. So this is very much similar to what Dougal was talking about. In fact, the ratio is basically 2 muscovite to 1 biotite in all these where we counted them up. So muscovite must be dissolving in the matrix and precipitating in the selvages. So the question is, can we model this? Can we do this quantitatively? I mean, we kind of know what's happening, but can we make more sense out of it in a quantitative way? And in the process, learn something about how rocks evolve. So, since we're talking about a kinetic process, we have to talk about rate limiting steps, which I've already mentioned, but I made a cartoon rock just to make this a little bit clearer in terms of what I'm talking about. Here's a rock that has chlorite and plagioclase and quartz, and here's a garnet. That's about the minimum rock you could have to actually grow a garnet with the various elements in it. But anyway, at a little straight point, you can have surface kinetics can be rate limiting, and I think in some cases they are. Surface kinetics can be rate limiting on the reactants or the products, and you can have diffusion limitations, either grain boundary diffusion or lattice diffusion. I think Dougal was saying that grain boundary diffusion was rate limiting, even though I don't know if he actually used that term. And the weird thing is grain boundary diffusion is much faster than lattice diffusion, right? It's orders of magnitude faster. But the key here is that you have to move enough material through the rock to make the garnet. And the grain boundaries are so small that even though it's going faster than lattice diffusion, it still takes a while to get there, and the process becomes rate limiting. So I'm assuming that grain boundary diffusion is rate limiting in this model, although that's not a necessary assumption. That's just where I've decided to start to get the mass flux. Okay, so the next thing I had to worry about was how to balance these reactions. Dougal had some balanced reactions. He balances based on aluminum being immobile. I don't think that's practical because if you look at a grain boundary and a quartz garnet contact, you're not going to make much garnet because there's not much aluminum there. You can balance on silicon, which I think Tom Foster likes to do. I don't know where Tom's sitting there someplace. You have the same problem with volume if you do this because you have oxygen, and oxygen's carrying a lot of volume with it. What I've decided to do, for better or for worse, is to balance the reactions on oxygen. And there's a couple reasons to do this. One is it's easy. you just write quartz as Si1/2O, and you write garnet with 1 oxygen and so on. But the other thing is it very nearly conserves volume. So I'm getting the volume conservation at the same time of making the calculations a bit easier. One could also write these conserving volume, but then that changes as the composition of the minerals change and the BT change and everything else. This is independent of changes of mineral composition. So, okay, so that's the way of balancing the reactions in this model. And when you do that, okay, so we got these various places in the rock. We got nucleated garnet. It's sitting there. And the way I'm imagining this model is that the rock starts off in perfect equilibrium with all these phases, quartz, chloride, plagioclase, in equilibrium with whatever's in the grain boundary. And then all of a sudden garnet nucleates. And garnet's obviously out of equilibrium, so it wants to react and grow. And so it's going to react with the quartz and the grain boundary stuff. And when it does, via this reaction here, what you find out is that the grain boundary gets depleted in certain elements. These are the ones going into the garnet, but it gets enriched in silicon. Okay, so we're changing the grain boundary composition by these local reactions. You can do the same thing for chloride, and when you react chloride's going to want to be consumed, and when you produce quartz from it, you deplete the grain boundary in silica, but enrich it in these other elements. You do the same with plagioclase, in which case you deplete the grain boundary in silica, but you enrich it in calcium, aluminum, and sodium. So you have all these processes going on. So the model, the way I conceptualize the model, is that you nucleate the garnet, and that disturbs the grain boundary composition right next to it, which sets up compositional gradients, which then allow diffusion to various everywhere else in the rock, which then sets up affinities at other interfaces between chloride and quartz here and plagioclase and quartz here, which then allow those reactions to go, which then change the grain boundary composition back at garnet, and the whole thing cycles along until. Well, here's the summary of those things. The whole thing cycles along until it gets equilibrium. Just to point out, no reaction can occur. Both phases are the same, simply because you can't write a reaction, an oxygen balance reaction. That's the answer to your question, Tom. Anyway, so, oh, what happened to that? Well, I'm going to have to use my pointer here. Yeah, there are a couple of lines on here which seem to disappear. The other question we had to figure out was, okay, when these reactions are going between whatever adjacent phases there are and the grain boundary, when does the reaction stop? And well, you can't see this here, but this is the free energy surface for garnet, and this is the free energy surface here for the grain boundary. And when you have a grain boundary out of equilibrium with garnet, you have a tangent plane to it. And you can draw another tangent plane, tangent to the garnet free energy surface. And if you draw those two tangent planes parallel, then the difference between where the tangent plane right where it's tangent to garnet is the change of free energy you will gain if you turn the matrix assemblages into garnet. This is exactly the same kind of diagram that Pierre showed earlier. Well, what we do is we start there, and that gives us a composition of garnet that we can use in our calculations, and we allow it to iterate until we get to the common tangent. So the reaction proceeds until the local equilibrium is attained. And I want to emphasize that the local equilibrium is happening in it's a nanoscale. We're not talking about equilibrium around a phase or anything. These are very small scale equilibria. I'm sorry about this. And we call this the maximum driving force approach because it's the maximum amount of free energy you can gain. It's also called the parallel tangent approach. Anyway, apologize for that, but that's how we drive the reactions. So that's when the local reactions stop. Okay, so just to summarize the model. The initial conditions are everything's in equilibrium, but there's no garnet. Then garnet nucleates and is out of equilibrium with the local grain boundary. And that's going to happen if you overstep a reaction. So whatever grows, you cannot get instantly to equilibrium. You have to go through some process. So these local reactions are set up initially next to garnet, and that proceeds until equilibrium is achieved. And then we get chemical gradients, which drives the grain boundary diffusion. And then the grain boundaries adjacent to the reactants are out of equilibrium, which then drives those local reactions, which then creates more gradients, which then changes the grain boundary composition next to the garnet. Well, you get the picture. You repeat this over and over again until eventually the whole rock gets to equilibrium. So this is the rocky road to equilibriums, I believe. Local equilibriums that are driven by local affinities, and then limited by grain boundary diffusion, and the whole thing goes on until eventually all the phases are in equilibrium. I mean, one way to think about this is, how does this garnet know that this chloride even exists and vice versa? And the only way it knows is by the grain boundary composition. When that grain boundary composition gets to be the same everywhere, and there's no more, and the affinities are all zero, then you're at equilibrium. Okay, well, how do we approach this in reality, right? So my first idea was, well, we got to make a grid. So here's my first attempt at a grid, nice hexagonal phases, 3 grain intersections, and so on. I thought, well, this is fairly easy to program because you can mathematically describe these things. But then I said, well, wait a minute. I want the garnets to start out small and grow. Here, this garnet is really big. So when I made the garnet small, it started to look pretty weird. And I also thought to myself, you know, I'd like people to look at this and says, oh yeah, that kind of looks like my rock. And I'd have a hard time imagining anybody in this room looking at that and saying, oh yeah, my rock looks like just like that. So I went to a different path, and and I came up with a method of basically drawing this thing in Illustrator and then parsing the SVG file and make this grid. So here's my first attempt at making something that looked a little more like a rock. If you can see the minerals, we've added muscovite and biotite to this. Plagioclase is over here, of course. It's a pretty sparse rock, but you know what I did was I started off with everything in equilibrium, but then added these garnets at various different places to see what difference it would make in the way they grew. How we do? Okay. Yeah. So this is the first model, and then you turn the program on, you run it for 6 or 8 hours, and hopefully you get close to equilibrium. Oops, I'm sorry. I mentioned one more thing I forgot to mention, was just that if you're wondering about this whole thing, the diffusion part was the easiest. It's one-dimensional diffusion, and we could do that in the back of an envelope, right? The only tricky part was when we got to these little 3 grain intersections, and I made up something, and I'm curious to know if anyone's seen this before. But when you got these 3 grain boundaries coming together, we want the change of composition to node. And all I did was I added together the 3 curvatures, which I think is correct. And it gives what looks like a reasonable answer. But if you know of anybody who's done this and derived this, let me know so I can cite them, and I don't have to take the blame for working this out. Okay, so that's that. And here's the initial conditions. Everything is in equilibrium, and we just nucleated the garnet. And then after cranking around for 10 hours, it looks like this. So we've grown garnet. It's hard to tell what else we've done here, but the garnets are bigger. So what I did on the next slide, so you can go between, oops, goodness, this thing is very sensitive. You can go between these two, but what I did here was I took the initial and final and superimposed them. So these kind of ugly green colors here are the initial size of the grains, and then the black ones are the final ones. So you can see a number of things. First of all, garnet is growing. Okay, that's good. That's what we expected because it was out of equilibrium. But it's not all growing the same amount in all the various places. This garnet down here, which is surrounded by quartz, has not grown as much as this one around biotite, which is eating into the biotite. Well, and that makes sense because the nutrients to grow garnet are right there. A lot of them are right there next to the biotite. This one over here next to chloride is also growing a lot for the same reason. Here, garnet is replacing muscovite, and down here it's replacing muscovite. So the amount of garnet growth depends on what phases it is and what the proximity of other phases is. The other thing is you can notice that, okay, muscovite, for example, is replacing plagioclase over here. It's replacing biotite here. But over here, muscovite is being replaced by garnet. And down here, too, muscovite is being replaced by garnet. So whether a phase grows or is consumed depends on who its neighbors are and what the distribution of other phases in the rock is. So muscovite is both growing and being consumed at different places in the rock. This starts to sound a lot like what Dougal Carmichael was getting at early on. And I was very hopeful and optimistic when I saw this. The other thing I do is at every one of these grid points, I save everything at every time step. Well, not every time step, but every 10 time step. Sorry. And so I can take the composition of any mineral here and plot it. And so what I did was I took the composition from one grid point from each garnet, and I plotted them up here against the radius, picking a center for the crystal. And you can see these don't look too bad. The spessartine decreases with the different garnets. It doesn't have the same composition as the rim of this garnet. Pyrope increases. These are exactly what we see as garnet grows. And this is all isothermal and isobaric. There's no change of P&T. And there's no Rayleigh fractionation in this model either. I'm not 100% sure exactly what is controlling the spessartine, but there it is. What's even more interesting is I plotted it here on the bottom against the model cycle, which is a proxy for time. So you pick a certain cycle, and that's what the model looks like at a certain time. And what you can see is that the spessartine content on the rim of the garnet, at the edge of the garnet, is not the same in every one of these. It's the lowest in this garnet number 1, which is up here next to the chloride. It's the highest in this garnet number 4 over here. I'm not exactly sure why this distribution is there, but clearly not all the garnets are getting all the nutrients they want in the same amount, which is a consequence of the grain boundary limitation on the rate. Eventually, these should all get to the same value when you get to equilibrium. That's sort of a given. Obviously, this model didn't run all the way to equilibrium. So I have another model, and this is Mach 1, and this one is Mach 2. It looks a little more like a rock, right? Maybe. I was trying to make some kind of pseudo-spoliation out of this. There's plastic-based biotite chloride. Here's a little garnet here. There's another garnet up here, another garnet over here, and another one down here surrounded by quartz. And we let this one run for a while. Oh, no, I wanted to show you the gridding. This, you end up with lots of, you have to calculate at every single point here. It starts to get pretty slow, but anyway, it does work. And you can just go home and have a beer and, anyway, so this is the final result. And I better go back here so you can see, like this really tiny garnet here, and there's another tiny one up there. Anyway, this is the final result. This one is weird. This garnet is kind of oozing out on this around this chloride, but that makes sense because the overall reaction is really chloride plus quartz goes to garnet. So it's got everything it needs, nothing that can move very far, and it's getting big. There is no control here on making these things crystallographically, dodecahedral-like. You might be able to add that in to make them look more like garnets, but in any case, it's certainly growing the most. The garnets elsewhere are growing to different amounts, as we saw before. I just want to show you a blow up of this one over here so you can see what garnet plagioclase are doing. And you can see that garnet is replacing plagioclase. It's also replacing the quartz. It's probably getting a lot of nutrients here from the biotite to do that, which doesn't have to go very far. But here are the plots of garnet composition versus radius. And you can see these compositions are all coming down nicely. They're getting close to similar values down here toward the end of the run. They're not all the same size, as you can tell. But here, where we look at the garnet composition versus cycle, we find that at any given time, there are different compositions. It's often said or used in looking at garnet zoning that manganese is a timeline. I don't know if you've seen papers like that, but if this is correct, then that means that's probably not a great assumption to assume that the same manganese in two different garnets represents the same point in time. But clearly, there's a lot of the parameter space that needs to be explored here. I would say very much a research in progress. Okay, well, that's the end of what I want to present. I just want to do a little shameless publicity and recruiting here. We have a grant. Ethan Baxter, Boston, is going to date some of these garnets. The idea is that if the ones with lots of garnets and the ones with a few garnets, if they really did nucleate at the same time, they should give the same age. So we're going to see how that works. If it does work, they're the same age, then it supports our interpretation. If they're different ages, we should be able to get something out of heating rates for it. So that's part of it. Jay Thomas at Syracuse is going to try to do some experiments to figure out how much overstepping it takes, at least in an experimental capsule, to nucleate garnet. And along the way, he's going to try to recalibrate some of the spessartine properties, which would be great for these databases and activity models for spessartine garnets. My job is more of the field work and the modeling. If you have samples that look anything like the ones I showed you earlier, I'd love to talk to you. We could certainly use more samples. And then I also should mention I have funding for a postdoc if anybody has got a year or so and they want to spend time doing this. Let me know. So, okay, thank you very much.
Very good. Time for a few questions.
Yeah, interesting stuff, and it's implicit in what you've done. Have you thought about more explicitly dealing with chemical potential variations on that local scale?
Well, any one of these, one could describe any one of these grid points with chemical potential.
Yeah, yeah.
So I haven't done that specifically because, well, actually, that's not true. The diffusion, it's all based on composition gradients, even though you could do it with chemical potential gradients. The chemical potentials are all defined where I have a reaction going on because that, you know, using the parallel tangent method, you basically set up the chemical potentials of all the components in both for both the matrix and the phases, and then you just solve for where they're parallel. And it's exactly the same way Ziriac domino approaches the problem, except they rotate everything horizontal first and then find the minimum. I just, you know, find the parallels. But yeah, so I haven't actually looked at specifically at chemical potentials to see what the values would be from one point to another. That might be interesting. I look at the affinity between the grain boundary and the garnet, but it might be interesting to see what the chemical potential gradient is as we go around the grid. Yeah, I know there's several papers where people have looked. Yeah, you are on one of those, and you know, looking at chemical potentials. Well, it's all, you know, chemical potentials and compositions are related by the activity model. So
Yeah, that's what I said. It's implicit in it.
Yeah.
Yeah.
I'm sorry, I think this was next. Yeah.
So, nice to see
Oh,
yeah.
So, thank you, very nice. I like that very much. Kind of setting up of your grain bounds. Of course, I have a question, but you're throwing away the quartz grain bound, double quartz grain bound. But if you really have quartz SiO2 gradients, it should react.
well, you write an oxygen balanced reaction with quartz in the grain boundary, and I'll put that in there. But I think that's the reason there's no.
Because you're fluid.
Well, yeah, but you're thinking of fluid. But you're thinking of fluid that has an oxygen in it. You want to take silicon plus oxygen in the fluid and make quartz out of it. There is no oxygen in my fluid. These atoms are bouncing along from one oxygen in quartz to another.
I understand that. I'm just saying, I think you would reduce the distance that SiO2 has to move by allowing the quartz to have some effect on the material flux on your grain bound.
Interesting idea. Yeah, I see what you're saying.
Oh, Tom, and then
Yeah, I mean, the problem I have with moving the silica along your quartz, if you've got quartz on one side or the other, is that you're assuming local equilibrium quartz. So the minute you hop an additional silicon into that grain boundary, it should precipitate.
But there's nothing to precipitate with. So you're thinking there's going to be water, that silica
Well,
plus
then
water
you're
could go to make quartz. What's that?
Then you're not in local equilibrium.
I'm sorry.
Then you're not in local equilibrium. That's
Well, no, we're just, since everything's balanced based on oxygen, there's no oxygen being transported around the system.
I was just talking about the silicon.
Yeah, no, I honestly think the silicon goes through unscathed. And, you know, you could precipitate it here and dissolve it over there, but how would it know? There's no way, it's not like an electric wire. You can say, okay, I just got a silicon, you can let them go there.
Gradient in your silicon,
Well, there is a gradient in the silicon which drives the diffusion. Yeah.
but not if you're in local equilibrium at constant temperature pressure with SiO2.
But I agree with you, except
I think there's a way around it.
no. My thinking is that if you can't write a chemical reaction, then there is no such thing as a delta G. I think that's fundamental thermodynamics, and you can't. If you could write a reaction in, but you're right. There's more silica here than there is there, and yet it reacts here and it doesn't react there. It's a weird concept, but I think I'm right. But we can talk about it later. Anyway,
my question was actually following up on the first question, as that implied chemical potential to be another factor in this. And I was wondering whether the maturation, so the larger crystals scavenging the smaller crystals would allow you to
like Oswald's ripening kind of a thing. Yeah, one could incorporate that in, and I have not really tried to do that. These systems are so far out of equilibrium when they start that everything wants to grow. And but at some point, when they get to equilibrium, then the kind of energy changes you'd see with Oswald's ripening, the surface areas, might take effect and allow the larger crystals to grow at the expense of the smaller ones. Yeah, no, that's a good idea. Another thing, I didn't mention this, but down the road, I think you could incorporate strain into this and actually evolve fabrics, which I'm rather excited to think about, but I have no idea how to do that now. But, since it is a totally discretized system, one could add almost anything you wanted to. Certainly strain energy in the nucleation, and with the growth of the crystals and regrowth. Could strain on a muscovite, which would dissolve and go someplace else.
Yeah, we've got time for one more question. Bernardo.
Frank, thank you very much. Do you think that eventually you can make your model grow a mineral even if its bulk amount is decreasing, like the muscovite replacing the garnet?
I think so. I hope so. We're sure going to try that, because I'm going to try to model that one thing I showed you and see if the muscovites in the matrix dissolve in order to replace that garnet. I have my fingers crossed, but next meeting, maybe I'll be able to tell you whether that works or not. But I want to do the Carmichael experiment too. I mean, that's another one I want to try, kyanite and nucleate garnet inside of with muscovite and kyanite with muscovite around, see what happens. I'm pretty sure it'll work just the way Carmichael said.